Okay, good evening to everybody. Thank you for coming to the talk today. Today I'm very pleased to have Dr. Domenic Forte from University of Florida joining us to deliver our monthly talk on cybersecurity. Domenic, I know Domenic for a long time. Actually, we kind of were peers. We part of, I mean, large part of our PhDs overlapped. And I have myself given a tutorial in the chess conference together with Domenic a few years back. He's one of the most accomplished researchers, young researchers in the field of hardware security, and we are extremely grateful that we had to organize the seminar. This invited talk, our November talk, had not been organized with all these end semester activities, exams, gradings, etc. And suddenly we remembered that we had to organize one in November. I emailed Domenic, and within a few minutes he kind of agreed to deliver the chat. So we are extremely grateful to him. So I'll just briefly read out his bio. So Dr. Domenic Forte is an associate professor and the Stephen A. Yataro Faculty Fellow with the Electrical and Computer Engineering Department at University of Florida. His research covers the domain of hardware security from nano devices to PCBs, where he has nearly 200 publications. Dr. Forte is a senior member of the IEEE, member of ACM, and serves on the organizing committees of top conferences in hardware security, such as HOST and Asian HOST. He has also serves and has served on the TPCs of DAC, ICCAD, NDSS, ITC, ISFA, BITAS, and many more. Dr. Forte is a recipient of the Presidential Early Career Award for Scientists and Engineers, the Early Career Award for Scientists and Engineers by Army Research Office, the NSA Faculty Early Career Development Program Award, and the ARO Young Investigator Award. His research has also been recognized with Best Paper Awards and nominations from IJCB, ISFA, HOST, DAC, and AHS. So thank you, Domenic, for agreeing to deliver the talk today. And it's your floor now. Okay, so attendees, I would request you that if you have any question, you can either type the questions in the chat box and we can discuss it if you do not want to ask it in person, or otherwise, please ask the question at the end of the talk. Thank you.
Thank you, Rajat, and thank you to you and the other organizers for inviting me today. It's a pleasure to be here. And thank you, of course, for the attendees for coming today. So today my presentation is going to focus on the benefits of reverse engineering for hardware assurance. So traditionally, cybersecurity is focused on software and networking, which rely on a trusted hardware assumption. However, that assumption is no longer accurate. So the hardware design flow basically works like this. We start generally with intellectual properties or IPs, which are either in a high-level language or an HDL. Those get used by SoC integrators and IC integrators who perform synthesis on them to get a gate-level netlist. They also combine them with their own in-house IPs. The synthesis can also optimize the design for area, power, and performance. After that, typically we have design for test and design for debug, which update the netlist for testing purposes later. And then finally, we have the last part of the design process is the physical layout, where the gates get translated into a series of shapes, which can be fabricated using lithography. And this design basically gets passed to a foundry who will fabricate it. Testing could occur there at the wafer level, followed by assembly where the chips get packaged and tested again. And then finally, these chips typically go to distributors where they reach companies when they get integrated into products or come to consumers themselves. Now today, most of the semiconductor IP, PCBs, ICs are designed, verified, manufactured, and tested all over the world. And very often, at least one of the entities in the process is untrusted. For example, third-party IP licensing became commonplace recently. And essentially what that means is that at the SoC integration step, they buy a lot of these third-party IPs from other companies, which could have trust issues. Another thing to point out here, which is shown on the top right, is that most of the advanced fabrication facilities are located in East Asia these days, China, Korea, Taiwan, and so on and so forth. And even many fabless companies are even outsourcing some of the design steps, other design steps today as well, such as design for test and even physical layout. And so the use of these third-party IPs and parties makes hardware design and fabrication more cost-effective, but comes with some security risks, as I'll discuss in the next couple of slides. One of the most notable risks are hardware Trojans, which are malicious modifications to hardware designs. A Trojan typically consists of a trigger as well as a payload, where the trigger is set to fire under very rare conditions, making it difficult to detect using conventional test techniques. And the payload is what causes the Trojan to perform some action. So it could act as a remote kill switch. It could cause leakage of the IC, make it operate unreliably or outside of its spec. And at an untrusted foundry, Trojan cells are easy to insert. Trojan trigger and payload cells can actually just replace some of these filler cells or spaces that are actually left in the layout for routing conditions. And this only requires a few modifications to the GDS2 masks. And these filler cells really are not going to be missed because they actually have no intrinsic functionality. There's also been lots of stories about state-level tampering, typically of PCBs, where there are two methods that are typically highlighted. The first is known as interdiction. This is where the electronics get intercepted in transit to their destination, and they get modified with some kind of a backdoor or tracker. The most popular example of this that I'm aware of was Edward Snowden's allegations that the NSA, the United States NSA, was modifying Cisco products that were being sent abroad. And the second mode occurs at the manufacturing source, and this enables even greater modifications. The biggest example of this was the Bloomberg article called The Big Hack, where Chinese spies allegedly implanted a chip which was the size of a grain of rice and disguised as a signal coupler, onto Supermicro server motherboards. And this chip basically acted as a backdoor to communicate with remote parties, allowing them to load all kinds of malicious codes and basically take over the server. And these motherboards were allegedly found in over 30 companies and government agencies, including Amazon and Apple, who were the two of the most profitable companies in the world. Another significant issue in the supply chain is counterfeiting. Counterfeit electronics are a problem that dates back thousands of years, and in electronics is becoming a bigger part of the counterfeit trade for the last 30 years or so. It's been said that about 10% of IT products worldwide are actually fake, and that this causes the industry $100 billion in sales annually. And there's many reasons for these trends. One is that the electronics and computing market is becoming more and more popular with all of our use of and ubiquity of electronics. And it's desirable for counterfeiters to ride that kind of wave. Another issue is that there's more waste than ever, and counterfeiters take advantage of this waste. So every time you throw away your smartphone or your laptop, the chips that are on it could actually be taken off those scrap PCBs and reinserted into the supply chain as if they're new. We also have a lot of critical infrastructures and systems that are aging and have decades-long lifetimes. Very often it's difficult to replace a lot of their components, which are obsolete. And this is a way for counterfeiters, again, to take advantage. So they could sell fake components, fake obsolete components at a very high price. And more recently, due to the pandemic, there's been a massive chip shortage that I'm sure everybody's been impacted by. And this is expected to only exacerbate counterfeits in the next couple of years. And so in the area of counterfeits, there's not a whole lot that you can do. The current best practice is to either use a subject matter expert to analyze the chips that you buy, or to procure lifetime buys for long-term maintenance. But then you have to predict how many chips you're going to need in the future. And the worst case is to just buy chips from untrusted or unauthorized distributors, because they're most likely to give you counterfeits. So all of these options are very non-ideal. So this leads us to reverse engineering, which is often considered in a harmful light, but I'm going to argue that it's one of the only foolproof ways to actually perform hardware assurance. So the hardware, the harmful applications of reverse engineering are shown on the left. It includes things like identification of exploits, development of attacks, IP theft and counterfeiting, which could all lead to either failures of critical systems or cyber attacks. And on the good side, as I mentioned, hardware assurance could be given by reverse engineering, where hardware assurance basically refers to these activities that ensure a level of confidence that the electronics function as intended and are free from known vulnerabilities. So on this reverse engineering side, as you can see, it's typically used for failure analysis, to assure the integrity, provide proof of IP infringement, assure authenticity, for example, counterfeit detection and Trojan detection, as well as to mitigate obsolescence, as we'll talk about more in the coming slides. But even though reverse engineer can help, there's a lot of questions and myths regarding how practical it is. So I'll try to dispel a lot of those throughout the presentation. And some of the ones that I'll focus on today are highlighted in blue. So first, people consider reverse engineering to be a destructive process, which can mean it would only be applied on a sampling basis. But as you'll see today, it is possible to perform reverse engineering on PCBs as well as firmware and software non-destructively. Second, it's viewed as time-consuming and expensive. And while this was true in the past, advanced procedures and instrumentation are beginning to change that. And third, traditional reverse engineering was a manual process in one or more of its steps, but it's becoming more and more automated today in both the physical process as well as the analysis steps. And with the rise of things like deep learning, we could expect this to improve even more. Now, compared to other methods of hardware assurance, reverse engineering has many benefits. First, it's the only way to actually establish a ground truth for other non-invasive techniques, especially when you consider commercial off-the-shelf or COTS components. Second, it could even be used to recreate and improve legacy electronics. And finally, it's less heavily impacted by process variations that could mask the effects of Trojans, counterfeits, and other things in non-invasive techniques. So the rest of the presentation is going to focus on some of the recent tools and advances in reverse engineering that we've made, and some of these ethical applications of reverse engineering. So we'll start with the state of PCB reverse engineering. So let me begin with just the conventional PCB reverse engineering flow. It's a destructive process, which starts with solder mask removal, where copper traces on the top and the bottom layers of the PCB basically get exposed. And PCBs are typically these multi-layer structures for our more advanced PCBs. And therefore, to actually get access to the traces and the features in internal layers, the board has to be delayered. This is a destructive process. It requires sanding, polishing, and things like that. And this is actually done iteratively, where imaging is used to obtain images from a single layer. Then we delayer to expose the next layer, where we image that, and so on and so forth. And once all of these images are obtained, they have to be processed using image processing and computer vision, sometimes machine learning as well, where they're segmented, and these segmented images can be interpreted into some kind of netlist. Now, obviously, the drawbacks of this process is that it is time-consuming and labor-intensive. And again, it has to be done in a destructive way. This means that the PCBs are actually unusable. And in some cases where the PCBs are scarce, like in the obsolete electronics that I discussed earlier, you may only have a few authentic devices in PCBs, and you wouldn't want to destroy them. So we've developed techniques that actually remove these destructive steps and can do this in a more elegant way. Our approach is based on X-ray CT, and in doing so, being non-destructive, we could assure that we could do inspection on every single system, which is very, very important for these high assurance systems. So it follows some similar steps, but the main difference is the beginning, where the sample, which in this case is a PCB, gets placed into the X-ray CT system, where it actually rotates while X-rays get passed through it and collected by a detector. These projected X-rays are given as input to reconstruction algorithms, which return a stack of 2D images or slices, which together form a 3D representation of the PCB. Then the remaining steps are very similar to what was discussed earlier. Basically, these images have to be analyzed, and they could be used to recover a netlist. So in the next couple of slides, I'll talk about some of the challenges we've encountered when trying to automate this process and how we overcame them. So this slide illustrates the first challenge. Basically, when the reconstruction algorithm returns a stack of 2D images, each slice can contain information from multiple layers. And this occurs because often the PCB is unavoidably tilted in the machine. And the effect of this misalignment is that when you proceed through the PCB and through these images in the Z direction, as you can see here, it results in information appearing on multiple slices from different layers. So this is shown here, where you can see this line is where we'd want the axes to be, but due to the tilting, the blue line shows that it's actually at an angle. And the loss of information is shown in the right-hand picture, where we can see that there's information in the middle of the image, but because of the tilt, there's actually some information from between two layers here and between two other layers in this corner. So the way that we get around this is by doing some kind of a realignment before we do our image analysis. Realignment would result in the PCB images looking like this, and therefore when we proceed through it, we get the information of one single layer in each image. So we developed an iterative approach to do this, where we calculate the center of mass and then the angle between the center of mass and the origin. The data gets rotated, and then this process repeats iteratively until the angle is within a very small threshold near zero. So you can see some of the iterations of our algorithm here for the X and Y directions, where the PCB is very tilted. And as you can see, after just a couple of iterations, it's very well aligned. And on the left, you can see two different PCBs. At the top, we have a Spartan 6 Xilinx board. And at the bottom, we have an in-house PCB, which we call RASC. Again, there's information that's actually missing on parts of these images. And then after alignment, as you can see, all the features of a single layer appear in the image for both of these designs, making them much crisper and clearer and easier to analyze. Another challenge is that we want to automatically identify how many layers are actually in the board. And this is very, very helpful for a lot of things, one of which is, for example, noise removal. So noise can be removed by actually averaging multiple slices of the same layer together. Having the critical number of layers is also important in identifying all the vias and traces on the board, because they could actually vary per layer. So we see some vias shown here in this cross section, where we have multiple different types. Some go through the entire PCB. Others start at one of the external layers, but only go to an internal layer. And some are completely buried. That is, they only appear in internal layers. And on the right side, you could actually see a PCB design shown in an editor, where there are multiple layers of traces shown in different colors: red, blue, aqua, yellow, green. And as you can see, a lot of them are overlapping because on different layers, they won't be intersecting. So for this reason, it's important to have all of this layer information, because we have to know how the PCB's components are actually connected to one another. So we developed a clustering algorithm that does this. It automatically determines first the number of layers and then groups the slices into each layer. So the images on the left show the ground truth for our in-house RASC board. And then the images on the right show the results of our clustering method. And you can see that there's a lot of very high correlation between the two. And the table in the center basically shows the quality of our results using three very common metrics: the SIFT intensity ratio, or SIR, the SSIM index, and of course just standard correlation. All of these values are very close to 1 for each of the layers, which indicates very high quality. And then for automated via detection, we developed a fairly elaborate scheme, which is shown in this slide, which we're constantly making improvements to, including the use of deep learning, which I won't discuss today. Our approach uses very little to no prior information. If the number of types of vias and their size is actually available, our algorithm can use that, but it's not necessarily needed. We also incorporate things like PCB design rules and optimization of templates of the vias to iteratively remove false positives, as you'll see. So in our first step, we do a tiered Huff circle detection algorithm because these vias tend to be circular in the PCB. The challenge, though, is that there's a lot of false positives, as you can see here. So these green circles, many of them are false positives. And so using some of the prior information, as I mentioned, such as different tier sizes, we can dramatically reduce the number of circles that are detected, as shown here, where we actually had 3 different tiers in this PCB: a large, a medium, and a small tier, shown in green, blue, and red. And then this allows us to remove these that don't actually exist in any of these tiers. And this is one of the first steps in removing these false positives, but there are still many other false positives as well. So in the next step, which starts our iterative process, we take a look at some of the pixels that are along these circle edges and try to remove those that have different intensities. We also transform the pixels into a bounding box for each of the circles, where we compare the intensity of the features to a radial template in the frequency domain. So this slide basically shows those 2 checks, where we have 3 different templates, which are taken and shown here. The first, again, is the pixel intensity of the circle. This basically removes the first sample, which, as you can see, is going to have a lot of non-white pixels. However, sample 3, which is not a via, has a lot of white pixels on its edge as well, so it's going to pass. But when we look at the radial template, the only one that passes is the one that's actually circular in nature, and that's the actual via. This also gives you an idea of how this radial template method works. So on each iteration of this algorithm, we're constantly removing false positives and then using those false positives and true positives to improve the probability density functions of each of them. And over time, we improve the actual template itself so that the distributions actually become more separated, making it better and better and actually learn and classify these vias better. We also do some mean shift clustering. This is just to merge nearby circles, as shown here. So we have lots of circles that are overlapping. This can just join them. And finally, we could also take advantage of the fact that a via is not going to just exist in one layer. It's going to exist in at least one adjacent layer. So we can actually use that information from multiple layers and combine that to also remove false positives. And finally, sometimes we get circles that look like, for example, this one, which are just an outline around a via, which basically means that it's not connected to this layer. Those circles that envelop other circles can also be removed, as shown here. So we applied our algorithm to 2 different cases. One is the Xilinx board shown earlier, which actually contains a lot of noise. And then the other one is the RASC board, which was our in-house board. We also compare the known and unknown via tier sizes so that we could see the performance of those. And here we use, again, a bunch of common segmentation metrics, such as intersection over union, or IOU, dice coefficient, and again, SSIM. Each metric has a value between 0 and 1. The closer to 1, obviously, the better. As you can see, the RASC board layers, which are imaged here, again, have a very high resolution and very little noise. And thus, when we look at the RASC layers, which are shown in the first two rows, we can see very, very high values, which are about 0.85 or greater, which is very close to 1. But even with the Spartan Xilinx board, which is shown in the final row, we still get values that are actually quite high, greater than 0.77 or so. And then when we compare the known and unknown columns, we can see that they're very much comparable across all these designs, meaning our algorithm is very robust, even without prior information. We've also recently been developing algorithms to automatically segment traces. Since this work is actually going to be presented at PAIN 2021 next week, I'll only briefly touch upon it here. So this approach actually performs pre-processing to first segment the entire image into these non-overlapping blocks, as you can see here. It extracts connected components, and then finally starts processing those components. One way to do that is to do ridge detection and to use the superpixels method, which creates basically a cluster of pixels. And then what we do is we analyze cycles in these pixels using graph algorithms. And from this, we're able to actually extract each of these traces independently, as well as the copper plating and these cutouts in the copper plating. There's also been significant advances in the automation of IC reverse engineering. So this slide shows the overall process for reverse engineering these ICs. Like a PCB, ICs are multi-layer structures as well, but unlike PCBs, there's not a scalable non-destructive approach for imaging them. This means that we still have to delayer each IC and image each layer one at a time. It's also worth pointing out that we use SEMs to do this imaging because the features are so small, and many images of each layer, maybe basically hundreds of thousands, often have to be collected and stitched together to create one large high-resolution image for the entire layer. Once we have these images, they need to be denoised and segmented, converted into shapes and vectors, from which we can actually annotate and analyze the netlist, similar to layout versus schematic methods that are used in design tools today. The bottom here shows a sample SEM image for a digital IC, where you can see these rows of standard cells. And a standard cell library typically only contains maybe 200 or 300 standard cells, and those basically get repeated throughout the design. So I've highlighted a bunch of those standard cells which are repeating here. So you can see a few buffers, a few NAND gates, even in a more complex AND or inverter standard cell. And once you have this information, you can combine it with the information of layers above it, which are basically metal lines connecting them, to get a netlist. So we'll talk a little bit more about the deprocessing step, where we've made advances in automating this process. But first, let me talk a little bit more about the conventional approach. This requires, of course, first that you depackage the IC, followed by steps that require multiple stations, which are often available in a clean room. This includes things like wet chemical etching, reactive ion etching, and then imaging. Some of these steps can be very messy and error prone, and as the sample, which is a die in this case, becomes thinner and thinner, it becomes more difficult to handle and actually transport between each of these instruments. This means that you may actually require multiple die to be deprocessed just to capture all the information properly. In 2017, though, we developed a new scheme, which was actually automated, and it only really required 2 instruments, one of which was only used for kind of a pre-processing step. So that first instrument was just basically a very advanced polisher, which thinned the die down to a few microns. And then once we had that sample, we actually proceeded through the backside and put this chip into a plasma FibSem, which is shown here. A plasma FibSem is a device that has basically two beams, one that could be used as a fib to basically remove or delayer material, and another, which is an SEM column, which could be used to do imaging. And our particular machine, which is from TestScan, is actually one that could be scripted. So what we can do is put our sample in the machine, and then it could be shifted to each column where we could remove material, image, remove material, image, and keep doing this. And this actually allows us to get even sublayer information if that's what's desired. And this is all done really in one instrument. This slide here basically shows an example of this, where let me see if I could run this video. Hopefully you could see this. This was done with our automated process. We start with the active layer shown here, and then you'll see metal 1, which is a lot of bright white lines. Following that, we'll go into metal 2. And then towards the end of the video, we start getting into metal 3. And again, this was all done automated on a sample in our lab. And we also have to talk a little bit about acquiring some of the images after we do this deprocessing. As I mentioned, there's lots of images that are actually acquired and need to be stitched together. If you were to do this imaging at the highest resolution for an advanced node, like say 14 nanometer, it would actually require hundreds of days to do all the imaging, just for one single layer. So in some of our work, what we developed is a routine that for at least parts of the IC takes low resolution images, which in areas that are actually less dense. So to do this, what we do is we take a low resolution image of parts of the die. We use an algorithm based on feature density, which determines which areas are dense and which have low density. In this image shown on the right here, you can see the dense regions are highlighted in red. That's what our algorithm detects. And these less dense regions, for example, these metal areas here, those are basically blue. And so that means in these blue areas, we can actually take images that are larger in size and therefore reduce the number of images we have to take. So what we found is that this could actually speed up imaging 40 to 60%, depending on how dense your IC design is. We've also seen some advances in the denoising and segmentation of IC images. What we've done is we've tried to deal with the noise by carefully looking at all the sources of noise in SEM images. These can be categories in material specific and human factors, where the imaging errors can involve the SEM imaging beam, its stage, and so on. It could also involve delayering errors or deprocessing errors, such as uneven delayering in the sample. Finally, the different materials and dimensions of the IC also charge differently under the SEM. This affects the intensity as well as the noise in the image. And it's worth pointing out that some of these sources of noise are completely random per sample, whereas others can be statistically modeled and characterized from the sample itself. So one algorithm that I'll show you here, which we call laser, actually utilized some of the noise that we found in the image. So the top left here shows if you applied a normal image intensity-based segmentation algorithm on an SEM image. As you can see here, there's basically two peaks, but if we actually manually segmented the image, you'll see that there's two, the foreground and the background, and there's a lot of overlap between the two. This would really be impossible to separate using an image intensity algorithm. However, what we found is that in our SEM images, each of the textures corresponding to different material have different types of noise, which form a texture. And using that, we can actually do a much better job of doing the segmentation as shown here. So here's an example of this as well. We have an original SEM image, a ground truth that we labeled manually. And then you can see three common algorithms for segmentation shown in red, as well as our approach shown in green. As you can see, our approach has considerably less noise than the others and has more continuous shapes corresponding to the features in this SEM image. The last part of IC reverse engineering that I'll briefly talk about is annotation. The first step that's really required here is to identify the standard cells, as I discussed earlier. Now, there's a lot of commercial tools that are available to actually do this, to recognize the patterns of these cells. However, to my knowledge, all of them require ground truth. They all need to know the standard cell library. And in some cases, that's not available, such as if you're reverse engineering a commercial off-the-shelf chip, you may not know what foundry produced it. So we've strived to try to do this step without actually requiring any prior information. And to do that, we took advantage of engrams, which are from natural language processing, and we applied them to these standard cells. We found that specifically the contact layer of advanced nodes has a lot of correlation in these engrams, and we use them to actually identify the standard cells. We basically encoded 3 features by comparing the distance between multiple columns, including them in our engram, as well as some of the distances between the vias in these as well. And then we developed some rules to kind of establish what makes a cell and what's the space between a cell. And what we found was that our algorithm was very highly effective for advanced nodes, where most of the standard cells were correctly extracted, and the ones that actually failed were typically ones that we didn't see very often. For 90 nanometer, we didn't do quite as well, and that's because there's lower correlation in these contacts. There's actually more correlation in the polysilicon for those layers. And this also brings us to the last component of hardware, which is firmware reverse engineering. So the hardware itself is not just restricted to gates, but also includes things like states, proprietary firmware, bit streams with respect to, for example, FPGAs. So it's not enough just to have the gates for hardware assurance. You have to have all the information in many cases to do a full-blown security analysis. So first, I'll highlight some of the work we've been doing in side channel disassembly. A side channel disassembler is something that takes side channel measurements, such as power consumption, EM, and so on, from a microprocessor or microcontroller, and then translates those traces of power or EM into instructions, basically the assembly code that's been running on the processor. So this slide contains a few examples shown at the bottom here. Here we have add shown in black and subtract shown in red for the same operands and data. And as you can see, there's a bit of a difference between the two of them, which can be distinguished using things like machine learning. We also find that even if we took the same instruction, such as an add, but changed some of its operands, like its registers, there's a big difference as well, which is even more distinguishable. And the last case is the case where we're looking at just modifying the data that's actually being used by the same instruction. In our case, we found that this was kind of too close, and we weren't able to interpret these. So our algorithm is shown here. It basically, again, takes the power traces from a predefined set of instruction classes and trains on them with a single device. These power traces then get mapped to time and frequency domain by continuous wavelet transform. And then we use Kullback-Leibler divergence, or KL divergence, to select features. These features are normalized, and they're reduced in dimensionality using PCA. We also do additional things, like to train the classifiers and decide boundaries and things. In some cases, we also deal with shifts that are caused by different devices, process variation, and things like that. We basically have a normalizing step for that too. And then what we do is we apply these classifiers to these traces to reverse engineer the code. And in order to reduce the number of classifiers that are needed, we take a hierarchical approach where we divide the instructions that are alike in terms of the elements that they're using in the hardware into different groups. Once we identify the group, we then apply classifiers within that group to determine the actual instruction. And then finally, we tried to figure out what registers were being used. and that involves additional classifiers. There's also subtleties with the traces that, again, we should be aware of. So the device that we worked on actually had a two-stage pipeline where we had to fetch and execute, and the majority of the instructions only took 2 clock cycles to execute, but a few of them, such as multiplication and branch, took multiple clock cycles. So what we had to do is develop training sequences to take this into account, and then our classifiers also had to take this into account. Here's a look at some of our results where we applied 4 different classifiers: neural networks, naive Bayes, support vector machine, and discriminant analysis. And as you can see here, even with very few variables, as few as 43 and about 60 or so, we can actually correctly determine the instruction, especially for QDA and SVM, with over 99% accuracy. The same, this was for the groups, this was for within a group. And then for identifying the registers, we actually do even better. As I discussed earlier, there's a big difference in those. So we again get 99% or better accuracy for those. Other methods I also like to touch on that are non-invasive but more advanced are optical probing or semi-invasive in nature. So optical probing focuses a laser beam on through the backside of an IC where the silicon is transparent, and takes measurements to recover signals in the device that are actually being processed. So very often this has actually been used for attacks to steal information like contents of SRAM and BBRAM, logic locking keys, cryptographic keys, bit streams of FPGAs, and so on. It could also be used to unmask circuits and by actually looking at the static values held in gates. But as I mentioned earlier, this process could also be used to extract information with more honest intentions, such as firmware of a obsolete device that you didn't design yourself, but you need to replace. So there's 4 different types of optical probing that I'll discuss in this slide. The first is known as LVP, or laser voltage probing. In this case, the laser remains focused on a particular location, and basically a waveform is extracted from that location. As you can see here, here's one of the waveforms. It looks very much like something you'd see in an oscilloscope. Then, for example, when the beam moves to this location, we get a very different waveform. And a key thing here is that in order to apply this technique, typically the device has to be run in a repetitive loop to improve the signal-noise ratio of these waveforms. The next one I'll talk about is known as LVI, or laser voltage imaging. In this case, the laser actually scans an area and produces an image. And basically the output of that scan is fed to a spectrum analyzer, which is set to operate at a specific frequency. What this does is that the image that gets produced has white areas which are basically switching at that particular frequency, and dark areas which are not switching at that frequency. Once again, this also has to be run in a loop to improve the signal-noise ratio of these images. And then on the bottom right, we have a new technique called logic laser state imaging, which is very advanced. This is the one that's been used to break mask circuits. Essentially, in this technique, it also produces an image. What happens is the clock gets frozen to keep the state of the logic static, and then the supply voltage is modulated at a low frequency, maybe a few hundred kilohertz to a few megahertz. And then what gets produced in the white spots, it basically shows the transistors in the device that are on. The areas that are black show the transistors that are off. And if you know what is actually located at where these transistors are located and what cell they belong to, you could use this to actually figure out what state is in the logic or what state is actually in memories on the device. And finally, we have TLS, or thermal laser stimulation, which is a little different from the others. The others work by putting the laser beam and capturing a reflection of that beam based on modulation that's occurring due to activity in the chip. But in TLS, the laser is actually used to stimulate different regions of the device to create local heating. This alters the current of the device, And this could be used to extract currents from very often from memories like SRAMs. And again, this could be used to non-invasively extract firmware and other contents. So by this point, I hope I've convinced you that automated hardware and firmware reverse engineering is somewhat feasible. And if not now, then in the very near future. The last set of slides here try to focus on what we can actually do with that information, especially with respect to hardware assurance. Now, I'll focus here on PCBs, but keep in mind that the same thing could be applied to ICs. So this shows a scenario that's very common that we encounter. This is when we basically have the PCB design, because we designed it. And what we're trying to verify is that the PCB that comes back from a fabrication facility is the one that we wanted. And it doesn't have any Trojans or other modifications. So what we do here is first do our imaging, for example, with optical images or again, X-ray, like I discussed. We do our processing and our segmentation to automatically extract vias and traces. And then we can automatically from there generate a CAD file. This CAD file can be compared to the original design file that we have. And if it's correct, we know that, or if there's very few variations, we know that this is an authentic PCB, hasn't been manipulated in any way or tampered. We also have the second case too, where there's some information available, but a little bit less. So this could, for example, apply to a COT system that you purchase and you purchase yourself. You purchase it from an authorized distributor and you take images of it. That's your authentic information. Then in the future, let's say you had an obsolete system, you would purchase another PCB, which is supposed to be the same, and you want to basically take images of it and compare those images to the original images that you had. You could also use these images to diagnose very common defects that could occur in PCB. So maybe the design is the same, but it's been tampered, or it's been soldered with very low quality instruments. So these types of defects can easily be found automatically as well. And this could again determine if you have a counterfeit or a Trojan infected chip. And obviously the last case is the hardest one. That's where you have little to no information. So in this case, you basically have to get the PCB, do your imaging, do your segmentation, diagnose your defects, generate your CAD files. And from there, there's things that you have to do that are more difficult because you don't have anything to compare to. So what are the types of things you can do? Well, you could try to diagnose those defects. Those are common things that may be easy to find. You could also use CAD tools, PCB design tools, to actually analyze the CAD file that you generate. You could look for things like cross-coupling, thermal hotspots, all kinds of other things that reliability analysis of these tools already handle. But you could also perhaps develop some security analysis things as well. Maybe look for things that are consistent with Trojans or something that's consistent with side channel attacks to see if there's a vulnerability and so on and so forth. And I'll also mention too here that we could again use this for obsolescence. So with these legacy PCBs, we could do our reverse engineering on them. And after that, we could do all this profiling, including the security analysis. And what this means is that the security analysis could uncover things that were flaws in the original design, such as low tolerance or low reliability in the face of fault injection or side channel attacks. And then you could actually propose to make improvements or upgrade this PCB. And this PCB can be improved, ideally automatically, but maybe manually today. And then it can be validated and verified, first with the same tools that we used earlier, and then actually in hardware. And again, this is very important for these legacy systems that have 30 to 50-year lifespans, like airplanes and trains. For those, the PCBs and ICs are scarcely found. They may no longer be available from the original manufacturer. So the only way to really get good ones is to analyze the good known chips and PCBs that we have and reproduce them in many cases on our own. Again, this will make you more tolerant, obviously, to Trojans if you do this in-house, but you could also mitigate past issues like I mentioned, with respect to fault injection, side channels, and so on and so forth. Just as an example too, there are some PCB security evaluation tools that are starting to crop up. So the two papers that I've highlighted here, they actually examine the power delivery network of these PCBs and use it to figure out if how easy faults can be injected, detect anomalies related to Trojans, and so on and so forth. These only really came into existence in the last few years or so, but more of these tools are being developed for both PCB and ICs. And this is very, very important for both analyzing potential flaws in them, both the ones that we design in-house, as well as, like I mentioned, these legacy designs that we reverse engineer ourselves. So just to summarize and give you some idea of what kind of work still needs to be done in this area, the presentation focused on security and assurance of hardware. We showed how IC, PCB, and firmware can actually be reverse engineered and support assurance, basically verifying that these match the original design. We could identify defects related to hardware Trojans and counterfeits, and we could even remake these obsolete systems. Now, future work should focus on addressing some of the major barriers that still exist in the areas, specifically in the area of automation. So the first thing I want to point out is that this is a multidisciplinary effort. It requires experts in VLSI, material science, computer vision, deep learning, and so on. However, most of these experts, they might not have access to either the equipment to acquire this kind of data or the samples themselves. So as a community, we need to do a better job of collecting this data and making it open source and publicly usable by these other experts who again, don't have access, but can maybe develop really good algorithms for automation. And related to this too, deep learning, which again is becoming very, very popular in recent years, it requires heavy amounts of data, hundreds of thousands of samples for training and testing. So this again illustrates why we need a lot more of these open source data sets. It's because even one group alone may not be able to acquire all of it, so we have to kind of share. So in our group, we've been trying to collect a lot of this data. It's available on TrustHub. We've also been developing tools that use that data to synthetically generate new data, which could again enhance the amount of information that we can use in these deep learning and machine learning algorithms. Second thing I'd also like to point out, and this is related to some of the tools I started talking about at the end of the presentation, we need more of these security analysis tools in general, but especially at the PCB level. At the IC level, more companies are starting to crop up that do this. Companies like, for example, Tortuga Logic, they've been developing tools to track information flow in IC designs and to detect unintentional bugs, as well as things like Trojans. So as a community, we could develop these tools which could be used pre-silicon to analyze our designs, as well as post-silicon to verify what we're getting back, or to analyze again these legacy designs. So before taking questions, I'd also like to take a moment to thank my collaborators and as well as the sponsors of our work, as well as our lab. Without them, we wouldn't be able to collect this data, to develop these algorithms, and to really test them thoroughly. So we're very, very thankful for all of this support. And with that, I thank everybody for their attention. Be happy to answer your questions.
Thank you, Domenic, for an excellent talk. So the floor is now open for questions and answers. Anybody has any question? You can either type in the chat box and I can read them out, or you can directly ask, raise your hand and ask for speaker privilege, and we can provide you that speaker privilege, and then you can ask the question if you are a guest. Oh, by the way, I think our department chair, Professor Dipanita Roy Chaudhary, is here. So, ma'am, if you are available, maybe you can switch on your cam once to say hi to Domenic. Is she here? Oh, I think she might have left the meeting. Anyways, I have a couple of questions. The first one is related to the X-ray based computed tomography, the first work that you started your talk with for PCBs. As far as I know, computed tomography is quite computationally intensive. It involves operations like radon transfer and transform and things like that, which are like quite involved. So I just wanted to know, like, what is the scalability for large volumes of PCBs of this approach?
That's an excellent question. So the imaging itself could take hours, on the order of maybe half a day for pretty big boards. Like, for example, the Spartan board, which is reasonably sized, maybe about 6 inches by 3 inches. I think that took about 10 hours to image. And then, as you mentioned, there's a lot of transforms that have to be applied, specifically for the reconstruction. That could take another few hours. And then our algorithms, the ones that we developed, are actually the quickest part. So they do this analysis very, very quickly. Some of the initial ones that we developed took a while, like maybe a day. But the deep learning ones that we're applying can now be performed in just a couple of minutes to extract all this information.
Okay, so are you looking at a threat model where it is sufficient to just take a sample from a manufactured lot and only test those samples, and it's not required to test every individual PCB from a lot? I mean, if that is the case, then I think this is fine. I mean,
yeah. When we're talking probably more about low volume applications, like government applications, army applications, things like that, where they may only be purchasing maybe 10 systems. So for them, they could run this process. They need the high assurance. But for the commercial case, for higher volume, you'd probably only apply it, like you said, on a sampling basis.
okay. And yeah, that was like that is also, your answer is also linked with my second question, which is like, given that at least at the current state of art, IC assurance seems to be, all the techniques seems to be destructive. So what, like, I mean, obviously you cannot apply it on the entire manufactured lot. You can only apply it on a small sample probably. So does like that?
Rajat, can you hear me? I lost you.
Hello. I think Rajat is somehow there's a connection. So hi Domenic, nice to see you.
Hi Debdeep, great to see you too.
Nice to see you, and excellent talk.
Yeah.
Yeah. So I just thought of.
Hello, Domenic.
Yeah, I just dropped, missed you, Rajat. I mean, maybe there's a comment like.
Oh, okay. Yeah, sorry. So I switched off my cam to save bandwidth probably. So my question was like the applicability of the assurance techniques for ICs for large volume. Maybe it is linked with the answer for the PCBs. I mean, it's a similar.
Yeah. For I think the difference between ICs and PCBs is, for the ICs, I mean, it's not impossible, but it's probably unlikely that you're going to have multiple masks being used for the same IC. So if you get, these chips back from a manufacturer, they're probably all going to be using the same mask. So you probably only have to apply it on one chip. And if you verify and authenticate that one chip, it probably applies to the rest. For PCBs, it's so easy to manufacture them and just modify the designs that you may have to apply it on a more rigorous basis.
And what is your opinion about proposals like split manufacturing, where basically you perform the IC fabrication partly in one fab and then maybe the metallization in another trusted fab or things like that? Like, is it practically feasible for general applications or?
I would say it depends. I think if they do make progress in 3D ICs, which at least I know DARPA is trying to push in the US, then that's a form of split manufacturing. And if they could make that viable, it could be very realistic. I mean, because then we could have these 2.5 and 3D ICs, and we could be, having them being partially built in multiple locations and then being put together. So that I think is pretty realistic, and those are much harder to attack and probably reverse engineer too, because you have to disassemble them first, right? So that would bring a whole lot of new challenges to us.
Okay.
So
Thank you.
I have one small question, Domenic. First of all, thank you very much for your excellent talk. So in our department, we are also trying to develop a facility on this kind of research topics, as I already told you before. And like we are largely initially starting with an invasive method, which is based on a ACM and FIB. And right now we are trying to see whether we can build using like XRMs, for example, for instance. So in this case, I have got a very, I would say like a not really like a very a directed question. Like there are different company vendors for XRMs, right? In particular, like with Carl Zeiss, for example, sells, right? Essentially, they have got very like good facilities on XRM machines. Likewise, I heard that there are some new sort of IPs which have come up as well, which essentially try to kind of reduce the time for tomography. Like for instance, I was hearing there is a company which is called as Prism, right? So do you can you make any comment, because sometimes like when you want to buy this and make this setup, then these are always difficult choices, right? Because they are very costly, right? At the end of the day. So any thoughts on this would be really useful.
Yeah, the most advanced instrument for SEM that I'm aware of is the multi-beam from Zeiss. So that one uses, I think it's up to like 50 beams to do the imaging, and it allows it to do it much faster at a higher resolution. So that's one of the ways of getting around this time it takes to acquire all the images. That's the most advanced instrument that I'm aware of. And in terms of like the X-ray CT stuff, I think most of these instruments that are out there right now were not created for this application. They were created to sample to X-ray larger samples like fossils and mechanical parts and things like that. But I do think that's going to change eventually, and we may get instruments and algorithms, reconstruction algorithms, that are more dedicated to this application. And I think my colleague, Professor Asadi, might even be working with a company to develop that kind of an instrument.
Okay. So